Afternoon all. Today we have the seventh lecture in the series on statistics in research methodology. Before we go into today's topic, we just have a quick summary of what we had discussed in the previous 6 lectures. We have to let you know. So we started with the introduction of statistics for the general case studies, introduction statistics in daily life and research. Then further, we had understood the various physical quantities, the ways to measure the physical quantities and the parameters which affect their measurements. Later on, we learned how to represent the results of measurement in the appropriate way so that the third person can appreciate the results of one particular measurement. Later on, we went ahead with accuracy and precision of measurements and did a few exercises to understand the difference between the two. Significant figures, place value of digits, rounding of error propagation, and the rules pertaining to all these have been discussed in detail. Later on, we went ahead with types of measurement errors, the sources of these various categories, namely gross, systematic, and random errors, and the ways to tackle the gross systematic errors. Finally, we came to the conclusion that random errors are unavoidable during any measurement. So you have to live along with them. At the same time, we can try to minimize the effect of random errors during measurements. For that, in order to understand the characteristics of repeated measurements, we studied in detail the properties of Gaussian distribution function, confidence level, confidence interval, and confidence limits were also explained during the 5th lecture. After learning about the Gaussian function and its properties and application to repeated measurements, we further had moved ahead with other continuous probability distribution functions like square. Starting from the point where we left in the previous class, the hypothesis testing and the areas corresponding to different parts of the probability distribution function. Let me go to the previous slide. Yes, this slide. This slide, the contents were discussed in detail. They are just a summary of the discussion we did in the last class. When we do hypothesis testing, it is to test whether a particular proposed experimental value is matching with the theoretical model. It can be applied in either two-way or one-way, two-tailed test or one-tailed test. One-tailed test can assume the form of either lower tailing or upper tailing. The entire thing is summarized in this slide. The center one is the two-tailed test, wherein the shaded portion corresponds to the rejection region of the null hypothesis. Null hypothesis generally puts in the form that the proposed value and the expected value, or the experimental value and the model predicted value, they match very well with each other. If at all there is a mismatch, that will be given by the shaded area in the curve. In all the three curves, in the central curve, you can see that the significance level, that is the region corresponding to the rejection region, and the area, unshaded area in the bell-shaped curve, that is a confidence level. Confidence level is normally obtained by taking a similar distance from the center portion, this mean value. Normally, if not mentioned, it is 95% confidence level corresponding to 5% significance level. That means if you are applying a two-tailed distribution test, on either side you will have 2.5% of the total area under the curve. That will correspond to the rejection region. So this curve is well understood by now all of us, which corresponds to Z value of 1.96 as can be read from the Z distribution or the normal probability distribution plot, as well as the table we discussed in the class before fifth lecture. If you go to the left-hand side curve of the screen, you will see that lower one-tail test can be easily applied for that portion, which corresponds to that area, 0.05 of the total area, when you consider a significance level of 5 corresponding to a confidence level of 95%. Here the Z value will correspond to minus 1.645. If you take 3 digits, if somewhere in the tables you will see only 2 digits after the decimal, it will be 1.65. The right side curve is also similar, as we have discussed in detail that the probability distribution function curve, normal curve, has got a symmetrical distribution of data. So whatever applies to the lower one tail with the other sign, alternate sign, that is positive sign in the right side curve. So here the Z value corresponds to plus 1.645, not minus. That you keep in mind. So the rejection regions are shaded in all the three curves, and the acceptance region will correspond to the confidence level. That is nothing but 1 minus significance level. In the last class, this was the one we left for discussion. Different types of t-test. Normally this parametric test, this parameter is called t. Parametric test is done in order to compare the value obtained by repeated measurements of a particular set of experiments to either a standard value or a known value, or sometimes a threshold value. If it is a known value where you do not have any idea about the distribution of the function, you apply two-tailed one. If you know that there is a threshold or a specification limit beyond which sometimes values are not expected, maybe above which only. If you have a idea regarding the functional contribution from the measured parameters, you can apply one-tailed test also. When we compare two independent means obtained by, say, if I am doing the analysis and somebody else is also doing the same analysis, we two are independent analysts. The results obtained by two of us can be compared using two sample tests. Two sample t-tests are done in two different ways that I will show you in the same slide after some time. Then if at all you want to check whether before doing some experimental conditions and after doing some modification in the condition, if that all there is a difference in the mean. The difference in the mean before and after the particular process or change in this particular steps of measurements, that also can be done via t-test. Then the form of the t statistic is slightly modified as shown in the box down. So this type of test is called paired t-test because the parameter, t values or the mean values obtained before and after these measurements, they are supposed to have some interdependence between each other. So it is a dependent parameter which we are checking for. Otherwise, generally, when we address a variable as a random variable, the attributes are independent. That is the assumption we normally take. In the case of two sample t-tests, when we are comparing two means obtained by either two sets of analysts or two sets of different instruments or two different methodologies, maybe you are adopting two new different methodologies you are proposing, then you can compare the performances. In that case, there are two different situations arising. One situation is that the standard deviations for the two sets of measurements, they are comparable. Comparable means of the same order of magnitude. Then you can use pooled standard deviation, which is given a symbol SP, pooled standard deviation, SP. The square of standard deviation is variance. Square of standard deviation equation also is given. And DF represents the degrees of freedom. Degrees of freedom also can be calculated if the two means which are being compared, independent means which are being compared, have comparable standard deviation. In the right side box, you go ahead with the arrow saying yes, if the two sample variances are equal. Go ahead with the arrow showing yes. If the variances are different, that means the standard deviations, order of magnitudes are different, then you have to consider independent separate standard deviations and do the calculations involved as shown here in the rightmost side where the arrow stating no goes ahead. That way you have to proceed. Depending on the magnitude of the standard deviation, one has to take a decision and use the appropriate t statistic to calculate the value. Once you calculate the t value, compare the value obtained using the measured value, calculated value, and if at all that calculated t value comes out to be less than the critical t value, the assumption of null hypothesis that the two means are identical becomes valid. If at all the t calculated is greater than the t critical, then the null hypothesis to be rejected. Go ahead with the alternate hypothesis. Here are a few examples for you to try working out to how to read the t table and get the critical values of t table. It is very easy, very simple for all of us. You know the number of replicates if you have in hand, degrees of freedom will be one number less than the number of replicate measurements. So if you have 3 replicates, degrees of freedom will be 2. And confidence level, if it is mentioned in percentage, significance level also can be mentioned in percentage. That will be nothing but 100 minus the value given. If the confidence level is given as fraction, it will be significance level will be 1 minus that fraction. So significance level value also you can fill in. And the t critical, you have to read as I told you in the previous class. If you know the degrees of freedom, come down in the first vertical column, first column in the table, given in the left-hand side, the T table. This is a typical general case of T table. There are different forms that I will show you in the next slide. This is a typical case wherein the degrees of freedoms are arranged from top to down in the ascending order. And at infinite number of degrees of freedom, you can see that almost as the degrees of freedom increases, the values of t keeps on decreasing. And ultimately, it will go and touch almost equivalent to the z value corresponding to the normal distribution function. T is another practical random distribution function of measurements. And as we had discussed in the previous class, one-tailed and two-tailed test also you can apply depending on the context of the experiment or the proposed model. Accordingly, you read out. If not mentioned, take it as two-tailed test. If there is no explicit mention regarding the type of test you have to apply, generally it is two-tailed one. Once you calculate the t value, one can calculate the confidence interval also. That is nothing but the horizontal axis value when you plot the normal probability distribution function as the parameter of the measured values with respect to the mu zero. Confidence interval for mu zero will be x bar plus or minus t into s by root n if we are taking x bar. If x bar is nothing but mean of repeated measurements. If you have only repeated measurements, you are not calculating the mean, then the equation forms like this, x plus minus ts. As we have seen, the standard deviation of mean is nothing but square root of like standard deviation divided square root of n. S by root n is the standard deviation for mean if you have n number of measurements. If you go to internet or literature or any statistics textbook, you will see that there are different forms, different ways of representation of the T tables. Somewhere you will see the cumulative probability function along with one tail, two tails separately mentioned. And if not mentioned, generally it is a two-tail test. Then some references, they give you the confidence levels also underneath in the table as shown in the left-hand side table. And somewhere the confidence levels may not be mentioned. It is nothing but 1 minus alpha, 1 minus significance level, if it is a fractional value. Normally, fractional values are given in the tables. Then, depending on the significance levels of significance, that will be decided from case to case. The variation will be there. If at all you are going for a stringent case, then as per the requirement, the significance level also will be decided upon. What should be the ideal significance level? That also we will discuss in the coming slides. Accordingly, one has to read the T table and take out the required critical values of T for reference and conclusions. As discussed in the previous lecture, we had planned to find out how many number of replicate measurements should be taken so that you get a reliable data from a set of experimental variables. Here in this table, this is a part of the table taken from the reported T values only. I have compiled here just for your understanding. One particular level of confidence, say 95% confidence level, the significance level will be 5% corresponding to an alpha of 0.05. So you read the second and third columns of this table. First column is significance level starting. First column is degrees of freedom from top to bottom, 1 to 20 are given. Second column corresponds to the values of T at a specific significance level of 5%. Then the third column is nothing but the percentage decrease in the value of T when the degrees of freedom are increased or raised up to that particular level. The original one is at 12.0706 original value. With reference to the original value of T, what percentage decrease you are getting? As the T values decrease, you will see that asymptotically it will go and touch with the Z values. The percentage decrease you can see initially there is a drastic improvement in the this decrement rate. Then later on marginal gain is only there. The fourth and fifth columns are similar compilation of data of T values corresponding to different degrees of freedom at 0.5% significance level corresponding to 0.005 of alpha. Similarly, the percentage decrease in the T values when we increase the degrees of freedom are compiled. The same data when you plot in the form of a graph, you can see that when the degrees of freedom increases, the value of T start decreasing drastically in the initial phases. And after say around 5 to 6 degrees of freedom, there is only marginal improvement, marginal variation in the T values as shown in all the three curves. When the T value is plotted against degrees of freedom or when the percentage decrease in T value is plotted against degrees of freedom, you will see that the change is marginal when you go beyond say 6 degrees of freedom. So 6 is a good enough number to catch up on with the T values, which will almost mimic the population parameters. If you have to get 6 degrees of freedom, there should be 7 repeated measurements. Practically, if at all you feel that it is difficult to do 7 repeated measurements prior to any reporting of data, maybe 4 to 5 will do. Even 4 degrees of freedom also will help us to have a fair justification regarding the parameters of standard deviation and T values. Ideal situation will be do repeated measurements up to 7 times. If not possible, go at least 5 times. If you are doing only 1 time, the variation is very large. You will see that the T values are very much numerically larger than the corresponding Z values. Normally, we apply the normal probability function or Gaussian function. Whereas if you do lower number of repeated measurements, you see that the variation or the disagreement between the T function and the Gaussian function is visibly high. Idea is to have a compromise between the experimental time as well as the quality of the data. If you want to have a compromise on both and you want to go ahead with fast output, definitely 4 to 5 repeated measurements would suffice for the purpose. But definitely not a single data. Singular measurements will not give you the real natural idea of the parameters. Now that you have understood how to read the T table, let us do this example. A sample of drinking water was analyzed for particular content, total chlorohydrocarbons. From the data obtained, you people can have a hands-on experience in calculating the 95% confidence interval. The data are given in terms of number of replicate measurements with the same values. Values are also tabulated with the ppb corresponds to parts per billion, the concentration of the chlorohydrocarbon. If you add up the number of replicate measurements, you will see that it comes out to be around 5 plus 7 plus 9 plus 8 plus 6 plus 6. 41 data points are there. But you have to calculate is the 95% confidence level. Since there are only limited number of data, we have to apply the t-test for doing the experiment. From the entire set of data, we can calculate the average value of the total chlorohydrocarbons in the analyzed sample. And since each of the individual contributor data are given, the standard deviation can be calculated. Further, from the T table, critical values of T in the table, we can see that the value corresponds to 2.021 for 40 degrees of freedom. There are 41 number of measurements. 41 minus 140 will be the degrees of freedom. Then you have to apply the equation that confidence interval will be equal to x plus or minus Ts. This equation you apply. That way you can calculate the confidence interval. And since we are seeing 95% confidence level, significance level will be 5, corresponding to a fractional value of 0.05. That way, the confidence interval can be calculated. All the steps are described in detail here. You all are requested to have a close check by doing yourself and get the feel of the same thing. From the value, as per the significance figure standard error propagation rules, we arrive at the value that confidence interval of the concentration of chlorohydrocarbons in the water sample after the rounding off and all the estimations will be 18 plus or minus 4 ppb. If you subtract 4, then it will be 14. If you add 4, it will be 22. So you can say that at 95% confidence level, the value will be between 14 and 22 ppb. Confidence interval will be 14 to 22 ppb. That will be final response for this question. This is another example to have worked out for T-table utilization. The following results were obtained for replicate determinations of calcium in limestone. There are around 5 such measurements. Each of these is the average of 5 replicate measurements. Then calculate the 95% confidence level as well as the 99% confidence interval. Confidence interval will be the range of horizontal axis values. Normally, when we do concentration determination, value will be concentration. So here it is in percentage. What you have to do, as we had done for the previous question, here since each value is coming out from repeated measurements and average, you have to apply the equation x bar plus minus Ts by root n. Accordingly, calculate the confidence interval, and for 95% confidence interval, you have to read the T table corresponding to a significance level of 0.01. That is 1%. And we can see that when we increase the confidence level or the confidence interval, the range, the value, the probability of getting the total area is also increasing. So the value, the spread in the value will also increase. So 14.37, the mean value remains the same. Only the confidence interval is larger when you apply higher confidence level. So you can have feel of all the things. In this third question, all of you may try yourself also. The answers are followed here itself. A chemist has obtained data for the alcohol content of a sample. Around 3 data points are given. The 95% confidence interval for the mean has to be calculated. Here we will see that if we apply the t-test or if we apply the z statistic, what is the difference? In the first part of the question, for the determination of confidence interval at 95%, 3 results obtained are only the indication of the precision of the method. That means we do not know the population statistics sigma. Here the question says that go and apply t-test. In the B part of the question, from the previous experience on hundreds of samples, we know that the standard deviation of the method is known and it is a good estimate of sigma. So the second part of the B part of the question asks you to go and refer to the Z table and apply accordingly. First part is to take help of the T table. Second part is to take help of the Z table. Calculations are simple. You have to do x bar plus or minus ts by root n in the case of T table, x bar plus or minus z sigma by root n for the Z table, for the utilization of the Z table. As you can see, when we go ahead from S to sigma, most of the time the value gets refined and the standard deviation gets better, precision gets better. So originally, when we had only a few limited number of data, 3 data, you can see that the standard deviation is around 0.005. But in the B part of the question, the standard deviation obtained over several hundreds of samples, you will see that the standard deviation is refined by getting 3 zeros after the decimal and 5.0005. Accordingly, when you calculate the confidence interval for the 2 different cases, you can see that the width of the confidence interval is confined. That means the precision is improved in the case of utilization of the Z table. Definitely, when you have larger number of data, when you do repeated measurements, the skill also improves as well as the quality of the data also improves. Hence, the precision improves. Only thing is that by repeated measurements, we are not getting improvement in terms of the other one, systematic error. Systematic error, one has to address alternatively, separately. Having addressed the systematic error properly, the refinement of data can be achieved by increasing the number of repeated measurements. That is what we are conveying through this exercise. And as we can see, for the same set of data, if we have sigma, you can do t-test also. Then you will see that the t values for finite number of measurements, t values are significantly higher for finite number of measurements. Then you will see that the confidence intervals are unexpectedly large if you use t-test in place where the z-test was more suitable. So there is always like a chance of getting different values when you use the 2 different tests. Here, another exercise in the same line you people can try. The new procedure was adopted for determining sulfur in kerosene. And the value of the sulfur, the amount of the sulfur in the kerosene sample is already determined, predetermined. There is a known value. And the repeated values obtained by the new procedure are listed here. Then, if you want to test whether there is a significant bias in the proposed new method at 2 different confidence levels or not. For example, if I do 95% confidence level evaluation, whether the newly proposed procedure is giving you reliable data without any systematic error or not. So t-test can be applied to understand whether there is any systematic error or not. T-test can be applied and you can come out with the result whether there is any systematic error. Because you know the population mean and the standard deviation of your value. Here, the first set, we had discussed the different types of t-tests in the third slide today. There we mentioned that comparison of a mean and experimental with known value. That particular equation we have to apply. X bar plus minus GS by root n will be the confidence interval. Once you calculate the confidence interval corresponding to a particular significance level, say 95% confidence level, corresponding to 0.055% of the significance level, the range or the confidence interval will come out to be 0.11 to 0.121%, whereas the actual value of sulfur is 0.123%. Since the confidence interval at 95% does not include the 0.123% sulfur value, there exists a bias, finite bias in the proposed new method if you do the evaluation at 95% confidence level. So if at all their specification limits are not given, generally we go for 95% confidence level evaluation. Then we say that there is a finite bias in the method. The method needs to be improved. If at all the specifications are not very stringent, you can go further ahead and apply the 99% confidence level. Then you will see that the confidence interval encompasses the value of the known value of 0.123%. So at 99% confidence level, bias of the experimental newly proposed method is not visible. This is what I wanted to convey. If at all the confidence levels are not mentioned, generally it is 95% we normally go. If at all for a specific case, you have relaxation or flexibility, wherein you want to include the newly proposed method data, you can enlarge the confidence interval and take this also, include this also. So there is finite level of disagreement when you take different levels of confidence in doing the hypothesis testing in the statistical analysis of data. What we conclude from that is that there is a finite chance of committing error or in concluding the data analysis and the reporting. There are two different sets of different types of such errors, which we call as type 1 and type 2 errors during the hypothesis testing. Hypothesis testing, normally we do propose a null hypothesis stating that the two values or the two means of the two data points obtained from different methodologies or two experimental and theoretical models, they match each other. That is the initial hypothesis. Later on, after statistical analysis, if we find that there is a significant disagreement or difference between the two, then we conclude that they do not match. That means alternative hypothesis wins over the null hypothesis. So in this case, where are the chances we are going to commit mistake during this hypothesis testing and further evaluation? That we will just see by looking through the curve also shown in the right hand side. Say, for example, if I have a mu1 value of 3.00, another mu2 of 3.05, and I propose the null hypothesis here should be mu1 is equal to mu2. That will be the null hypothesis. It is not mu1 equal to 3.0. Null hypothesis is mu1 equal to mu2. Then the difference is 0. Mu1 minus mu2 is 0. The critical value is calculated by having the confidence interval value. Then you can see that if you do repeated measurements to achieve mu1, that is 3.0, you will have a distribution of the data corresponding to the probability distribution of Gaussian function. Similarly, mu2 also will have a similar distribution. The area, if I set a confidence level of 95%, 5% of the total area is out of the consideration zone for mu1. So the darker blue portion, darker blue shaded portion corresponds to the area which is not under consideration in the confidence interval for mu1. And the lighter blue area which is not part of the population for mu2 when you take certain specific confidence level for mu2. The darker blue portion which is rejected when we say that the mu1 does not include that darker blue portion, that is called the region which we are rejecting the null hypothesis. That is the type 1, that is where we lose the data as part, even though it was part of the population, original population. The area or the probability corresponding to this region is called the alpha error or the type 1 error. Alpha is the significance level corresponding to that. Similarly, for the upper curve, wherein mu2 is equal to 3.05, there is a region where you will see that a lighter blue shading is given, which we consider as not a part of the set 2 data. This region where we take it as non-constituent of that second set, we call it as type 2 error. I'll explain it in detail in the coming slides again. When a particular data or a point or an area is rejected with respect to the null hypothesis, it is not part of the original population, we call it as type 1. Rejection of null hypothesis, the area corresponding to the rejection of null hypothesis, that is nothing but the significance level for a particular set of data. One general example is given as an innocent person during court decision, and an innocent person is being convicted. Though he was innocent, he is considered to have committed some crime. So that portion is corresponding to this darker blue region. When we say that alternative hypothesis wins over the null hypothesis, that is type 2, the second population, which is independent of the first one, then we see that there is a region, the probability area, which is taken out as not part of the second population, mu2 corresponding to 3.05, where we are wrongly rejecting the null hypothesis. This portion is called the beta portion of the second curve. This type of error is called type 2 error. Falsely, we are considering it as not a part of the second population. False rejection, false negative of the alternative hypothesis. So this is like a guilty person being released during the court decision. So that way you can simply compare between type 1 and type 2 errors. Idea is to minimize the effects due to either of these two factors, either type 1 or type 2. However, you will see that when you go ahead to minimize the type 1, when you make the tail portion of the first curve, lower left curve to minimize, you will see that at that effort, the tail portion, lower tail portion of the upper curve goes on increasing. So there is, like, we have to do a compromise between these two. And be informed that no test procedure can guarantee that we will not commit any mistake. Errors are bound to happen when you do measurement. Errors are bound to happen. Only thing is that you can properly judge the measurement results and come out with minimum errors possible from your side. So that way one can develop skill and come out with meaningful data. Error possibilities are the results of using a sample of data to make inferences about the population. That is clear. When we have a large number of data, statistics helps us to do the analysis, entire analysis, by taking a representative portion of the entire sample. However larger effort you do, it may so happen that sometimes whatever representative portion you have taken from the entire population is not a true representative of the entire one. Definitely, this mismatch will lead to error also. That mismatch one has to anticipate while extrapolating to the population. So initially, just by looking at the curve, at first thought we may think that if you want to minimize the alpha portion, darker blue region, then what you can do? Put the vertical line on towards more right. But at the same time, what you will be doing, the type 2 error, that is lighter blue shaded region, keeps on increasing. So you have to make a judgment so that you can have a compromise between alpha and beta error in the minimalistic possible way. General conclusion in the general case is that convicting an innocent person is usually considered as a more serious sin than setting a guilty person free. This is case to case dependent, whether to compromise on type 1 or type 2 error. That depends on the specific instances where you are applying it to. In the general cases, in the common cases, as described here, type 1 error, committing a type 1 error is more serious. But many times in practical cases, you will see that a compromise or a combination of minimum of alpha and along with whatever possible for alpha. It will be depending on the requirement, whether you can afford to have a minimum alpha or you can have a compromise between a combination of two. And most of the time when you are at the specification limit or at the decision level, you will see these curves always have some overlap. And as we discussed earlier also, this normal probability distribution function, it is asymptotic to the horizontal axis. Definitely there will be an overlap of two such parametric distributions. As we discussed in the previous slide, there are 4 cases of errors in hypothesis testing, and even when you do the correct decisions, you will see that there is a finite portion which is missing out from the final calculation of the total area under the curve. If the null hypothesis is true and we accept it, that means the decision is correct. That encompasses a certain level of confidence level. The second case is that the null hypothesis is true, which corresponds to the blue shaded region in the right side curve, alpha region, and we are rejecting. The idea is to minimize this tail portion. At the same time, when in the third case, you will see that when the null hypothesis is false, that means the curve H2 or the alternative hypothesis H1 is having predominance over your data, then we are accepting it. Even though the null hypothesis is false, you are accepting it. So that will correspond to the red shaded region in the curve shown on the right side. This is called the type 2 error, committing a type 2 error during the hypothesis testing. And the unshaded portion on the right hand side curve, that corresponds to the correct decision of accepting that the null hypothesis is false. Population H1 is different from population H2. So in the curve shown on the right hand side, the unshaded portions correspond to the correct decision part, and the shaded portion, blue one, corresponds to incorrect decision of false positive. Red shaded portion corresponds to false negative, type 2 or beta error. The same thing is summarized in tabular form over here. Type 1 error corresponds to false positive conclusion, or the probability corresponding to that area under the curve is alpha. And the type 2 error, committing type 2 error, that is a false negative assumption of the hypothesis. The area under the curve is given by the probability beta. Normally, these are the terminologies or symbols used in statistics till date. Generally, we can say that the largest alpha that is tolerable, largest alpha tolerable for a particular situation should be used. General rule, you can say that the alpha, which is largest, so set the dotted line in the curve such that the largest alpha tolerable can be utilized. So at the same time, there will be a compromise in the beta part. So this ensures that if you go for larger alpha, beta part or type 2 error will be minimum. It will be a combination of both together. If not mentioned the case, generally the alpha value is said to be 0.05. That is 95% confidence level. If not explicitly mentioned, general case is that go for alpha of 0.05. That is the acceptable compromise as on today. This is a set of example for you to appreciate the same type 1 and type 2 error very easily. For example, if a person is getting tested for COVID-19 with having mild symptoms, but he is not sure whether he has got affected or not. There are two such cases may occur. In the first case, the test result says that he has COVID-19, but truly speaking, he does not. This will entail to the false positive, that is type 1 error or the alpha error. The other case, even though the test result says that he does not have, but he is actually affected by COVID-19. That is false negative. Here in this case, it is better to go even though he is not getting diagnosed as a COVID patient, he is truly affected. The second case, that is more dangerous. So here in this case, second case is dangerous. False negative assumption is dangerous. So it all depends on case to case where you have to take a decision. If it is a general statement, you can say that let us have the minimum possible total outcome of alpha plus beta. So which error to be minimized, type 1 or type 2? As I told you repeatedly, it will be dependent on case to case. The probability of type 1 error is usually determined. Generally, the case is that alpha is given dominance. So alpha can be determined or decided in advance. Accordingly, we can set the level of alpha. Generally, we keep the level at 5%. That means 0.05 as the alpha level. Accordingly, type 2 error will get modified, whatever value is there. So if I fix the alpha level at 5%, definitely corresponding to that, you will have a beta error. If we fix an alpha at 1%, that means you are extending the you are reducing the upper tail portion of the lower curve, then you will see that the beta error start dominating over the other one. So if you can afford with increased beta level, then you may move the dotted line to upper level also. It is very well clear that when we have a fixed number of samples, fixed sample size n, then when we try to reduce type 1 error, the probability of committing type 2 error increases accordingly. So both these errors cannot be reduced simultaneously. Then what you have to do is to have a trade-off between both these type of errors. So while trying to minimize alpha error, definitely beta error is going to get high up. In those cases, whenever one has to take decision to decide upon which type of error should be minimized, it all will be dependent on the cost per experiment, cost per analysis, or sometimes what is the penalty you are going to get out of that decision. It will be a compromise or it will be a combined final decision based on the cost or time or instrument or the equipment, the penalty you are going to do to get from that entire set of measurements. One example is given here. If at all a type 1 error involves a time and trouble of reworking a batch of chemicals that should have been accepted, whereas in the type 2 error, it will be like taking a chance that an entire group of users of this chemical compound will be poisoned. Then in such cases, one should prefer type 1, like doing the entire job, repeating the entire job so that the second case of entire set of people getting poisoned can be avoided. It all will be like from your intuition as well as the requirement of a specific case, the decision has to be taken. That is why the decision makers should have a fair idea regarding the importance of the implication of these two different types of errors. So one must set a very high level of type 1 in this case in order to save the lives of persons in the case of chemical being harmed. So in the testing of hypothesis, one must take all possible efforts to strike an adequate balance between these two types of errors. It is all case dependent. As I told you, it comes out to be very crucial when you are at the verge of taking a decision, at the verge of decision making. If you can say that you are having particular result wherein some measurement is absent, which is shown in the blue curve. Measurement is absent, but when you put a significance level of alpha for the blue curve, you will see that the right side of the right tail of the blue curve, which is ahead of the dotted line here, this dotted line, you will see that the alpha value of 0.05 is represented here. If at all in a particular alternate measurement or another set of chemicals, you will see that the distribution of measured values is shown in the red curve, wherein the person reports that the measurement is present. The repeated data distribution will be shown by the red curve. You see that there is a finite overlapping region which is below this dotted line. The red curve, around 50% of the lower half, 50% of the entire curve, the lower full half is overlapping with the region of the blue curve, corresponding to an alpha of 0.05 for the blue curve. So what happens is that false negative or type 2 error is largely around 50% if you are at this dotted line of decision making. So you can see that at the limit of decision, the chances of committing alpha error is only 5%. But the chances of committing beta error falsely concluding that the analyte or the measurement is absent is 50%. That means the total error will be 50 plus 5, 55%. So this portion, it is very difficult to take a decision. This is called the limit of decision. A sample could contain an analyte at the limit of decision, but there is a 50% chance that the measurement would give result less than the limit of decision. That means 50% of the measurements you are falsely taking the conclusion. This area alpha equal to 0.05 corresponds to a sigma Z value of 1.65, as all of you can refer to the Z probability, normal probability distribution curve shown in the 5th lecture. The tables are also shown here. So if you set a 0.05 significance level, which will correspond to 95% confidence level, the Z value will be 1.65. You people can have a cross check with your data in the table. But when we move the red curve towards higher or larger or later part towards the right side, you will see that we will reach a point in which this central dotted line correspond to. Keeping the alpha error at 0.05 only, we are now kicking the red line towards the upper side. Then what will happen? A point we will reach wherein the beta corresponding to that upper portion, beta error, type 2 error also will be 0.05. Alpha equal to beta equal to 0.05. The maximum point corresponding to this red curve, the mean of the red curve, when alpha equal to beta equal to 0.05 with reference to the mean of the blue curve, that we call as limit of detection. So this distance will correspond to limit of detection. So when you do the instrumental analysis, a person or a company or a manufacturer quotes the limits of detection of a measuring device as nothing but the average of the blank plus 3.3 times sigma of the blank or standard deviation of the blank. This 3.3 comes from 1.65 of corresponding to alpha and another 1.65 corresponding to beta error of the red curve. So that corresponds to 3.3. the number 3.3 comes from the summation of the two area under the curves corresponding to the normal probability of normal probability distribution function having confidence level 95%, which is nothing but alpha of 5% or 0.05 in fractional terms. Now that we have understood hypothesis testing and type 1 and type 2 error, what we conclude from the hypothesis testing is that whether during the measurement, whether you have committed any particular error, mistake, or whether you have come to the correct conclusion. Initially, we state the hypothesis null as well as alternative hypothesis, then specify the significance level alpha, then later on we decide which sampling distribution. We have discussed Gaussian, rectangular, triangular for the continuous variables, and for discrete variables, binomial, Poisson, and Bernoulli distributions. There are very many other distributions also reported, but these are the ones we generally utilize during statistical analysis of data in science and research. Then in the third step, it will be the calculation of sample mean and standard deviation from the collected data. Then we compare the sample mean and standard deviation with the population mean. Here the statement you read through thoroughly, it is the other way around. The chances of sample mean or standard deviation being away from the population mean, that way the hypothesis is slightly modified. If this probability is smaller than the critical value in the case of one-tailed test, then you reject the H0 and the probability corresponding to this alpha is the type 1 error. If at all you accept the null hypothesis, then the probability corresponding to this type of error will be the type 2 error. This way, the entire flow diagram of hypothesis testing goes generally. We have learned Z and T probability distributions and the application in various cases with a few of the worked out examples. Later on, we will go ahead with other hypothesis testings and the other statistical parameters also. Everywhere, the flow diagram remains the same. Whether you test Z, T, Q, F or variance, the flow diagram remains the same. Put in the null hypothesis as well as alternative hypothesis, specify the significance level, then the distribution, the calculation of the required parameters, comparison with the population parameters, and taking like final decision whether accept the null hypothesis or go ahead with the alternative hypothesis. Accordingly, the fractional contribution from either type of error will be going along with your measurement results. Ultimately, the idea is to minimize their contribution. How we can minimize? By increasing the number of data points as well as rechecking each and every step of this analysis. Here we stop for the day. Any doubt or clarification is required, please start typing in the chat box. If at all there is any already written, I'll address those. If anybody wants any clarification, please start writing in the chat box. Otherwise, I'll summarize the day's class. We had started with the hypothesis testing and the areas corresponding to different tests like Z and T. Then we had seen different types, different utilities of the t-test. Then the confidence levels, confidence intervals calculated using T as well as Z statistic and seen the difference, which one is better, and as per the requirement you take a decision. And when in the case of a wrong decision, what are the chances of committing errors? We have discussed two different types of error, type 1 and type 2, alternatively called alpha and beta errors. Then how do we have a compromise between the two errors? And at the point of limit of decision, what will be the contribution from alpha error? What will be the contribution from beta error? And at the limit of detection, what will be the contribution from each of these two? So from the limit of detection onwards, one can start telling that yes, the measurand is present or not. At the limit of decision, it is difficult to have an inference of saying that measurement is absent or present. Limit of detection is the point above which one can confidently tell about the presence of a measurement. This is what we discussed today. And finally, we have seen the flow chart of how the hypothesis testing is done. If there is no doubt, we will wind up for the day. No doubts are seen in the screen. Okay, then we'll meet on 16. Okay.